Welcome to the General Chemistry 1 class. This section is on electronic structure of atoms, focusing on the electron configuration. In this lesson, we will write the electron configuration of atoms. Whenever you are asked of your address, you specify the complete details leading to your house, or unit number, street, subdivision, town or city, province, or sometimes postal code. As the case of electron in an element, there is a systematic way to tell us where a certain electron is found relatively closer or farther to the nucleus. The scheme used to locate the electron is called the electron configuration. Electron configuration is the notation used to represent how electrons are distributed in different energy levels or orbitals of an atom. It consists of subshells and the number of electrons found on those subshells. When electrons are at their lowest energy state, the corresponding electron configuration is referred to as the ground state electron configuration. In this lesson, the electron configurations we will write refer to those in which electrons are in the ground state. When electrons are in the ground state, it is made sure that each electron occupies orbitals having the lowest possible energy. The electron of hydrogen in the ground state is at 1s orbital. Thus, its electron configuration is given by 1s1. The first appearing number 1 corresponds to the principal quantum numbers or n. S corresponds to the azimuthal quantum numbers. I, which is the case, is equal to 0. And the superscript 1 is the number of electrons in the 1s orbital. For elements other than hydrogen, the following rules are considered in distributing electrons in different orbitals in a way that energy is minimized. Abfall principle, Pauli exclusion principle, and Hund's rule. We will focus only on the first two rules. The Hund's rule will be discussed later in another lesson. Abfall principle. Electrons fill first the orbital with the lowest energy before those with higher energy levels. Aufbau is a German word for construction or building up. Energy is minimized when electrons occupies the orbital or subshell with the lowest energy. Orbital energies. Hydrogen. In hydrogen, orbital with higher principal quantum number have greater energies than those with lower principal quantum numbers. If the electron is drawn closer to the nucleus, attractive force between these particles are greater, resulting in lower or more negative energy. For instances, the order of increasing energies of orbitals with different n values are 1s is less than to 2s, 2s is less than to 3s, 3s is less than to 4s, and so on. And 2p is less than to 3p, 3p is less than to 4p, and so on. On the other hand, no difference in energy is observed if the electron of hydrogen occupies any subshell within the same shell, even though different orbitals depict different electron densities. Thus, the energy of electron in the 2s subshell is the same as its energy in the 2p subshell. Likewise, the energies in 3s, 3p, and 3d subshells are the same, as well as for the 4s, 4p, 4d, and 4f subshell. Thus, the subshell of hydrogen arranged in order of increasing energy has the following sequence. 1s less than 2s is equal to 2p less than 3s is equal to 3p is equal to 3d less than 4s is equal to 4p is equal to 4d is equal to 4f, and so on. Electron atoms. In the case of atoms with two or more electrons, not only the principal quantum number affect the energy of orbital but also the angular momentum quantum number. Moreover, each orbital can be filled up with two electrons with this repulsion between these electrons that can affect the energy of electrons. The n plus 1 rule, a way to compare energies of subshells of many electron atoms, is through the Kleikowski rule, more known as the n plus I rule. To apply this rule, identify the corresponding n and I values of the given subshells. find the sum of these values, the subshells with higher n plus 1 value is higher in energy. If subshells have the same n plus I value with one higher n has the higher energy. Example number 1. Consider 1s, 2s, 2p, 3s, 3p, 3d, and 4s subshells. Use the n plus I rule to arrange these subshells in order of increasing energy. Solution. Tabulated on the right are the n and I values of the given subshells and their corresponding n plus I values. Emphasize that some subshells have the same n plus I values, such as 2p and 3s, with a value of 3, and 3p and 4s with a value of 4. To resolve this case, we should look for the n values of these subshells for 2p and 3s. 3s has the greater value of n, thus it has greater energy than 2p, while for 3p and 4s has the higher n, thus it has a greater energy than 3p. With this, the subshells arranged in order of increasing energy is given by 1s is less than to 2s, 2s is less than to 2p, 2p is less than to 3s, 3s is less than to 3p, 3p is less than to 4s, and 4s is less than to 3d. The scheme shown on the right is a useful mnemonic showing the order of subshells filing. To use this, start from the topmost arrow and follow its direction before proceeding to the next arrow. Principle. In the previous lesson, we have learned that no two electrons can have the same set of 4 quantum numbers. As a sequence, an orbital can be filled up with 2 electrons. The s subshells can be occupied with a maximum of 2 electrons, the p subshells with up to 6 electrons, d with up to 10 electrons, and f with up to 14 electrons. The electron configuration. Here are the steps. Step 1. Determine the number of electrons in the atom. For atoms, the atomic number Z is the same as the number of electrons. For cations, number of electrons is equal to Z minus magnitude of the charge. For anions, number of electrons is equal to Z plus magnitude of charge. Step 2. Fill the subshells arranged in order of increasing energy with electrons. Make sure that each subshells cannot hold electrons beyond the maximum allowed quantity. Write the electron configuration of neon Z is equal to 10. Solution. Consider the given mnemonic device for the sequence of orbitals to be filled with electrons. 10 electrons. Start filing 1s, then 2s, and so on until all electrons have distributed. Notice that the last electron ends up at the 2p subshells. This means subshells beyond 2p are omitted. Thus, the electron configuration is given by 1s2, 2s2, 2p6. 3. Write the electron configuration of sulfur Z is equal to 16. Solution. Consider the given mnemonic for the sequence of the orbitals to be filled up with electrons. In electrons, start by filling 1s, then 2s, and so on until all electrons have been distributed. Notice that the last electron is at the 3p subshell, implying that subshells beyond 3p are omitted. Thus, the electron configuration is given by 1s2, 2s2, 2p6, 3s2, and 3p4. In the previous example, our condensed electron configuration, there are 2 ways to write the electron configuration. As core abbreviated electron configuration is a shorthand notation for writing the electron configuration. Moreover, this notation is used to determine the core or inner and the valence or the outmost electrons. The core electrons correspond to the number of electrons of the elements under the rightmost column of the periodic table, known as the noble gas. The noble gases are helium, neon, argon, krypton, xenon, and radon. In writing the noble gas core abbreviated electron configurations, The electron configuration of the core electrons is abbreviated as the chemical symbol of the nearest preceding noble gas that is enclosed in square brackets. The core is followed by the electron configuration of the valence electron. Gas abbreviated electron configuration of neon. Note that only noble gas that comes before it. Note that helium has two electron configuration, thus the 1s2 portion of the electron configuration of neon can be written as He. With this, the noble gas abbreviated electron configuration is given by He 2s2 2p6. Case of sulfur, the closest noble gas that comes before it is neon with 10 electrons. The configuration 1s2 2s2 2p6 can be shortened as Ne. Thus, the noble gas core abbreviated electron configuration is given by Ne 3s2 3p4. Standard electron configuration is used to show how electrons, usually the valence electrons, fill each of the degenated orbitals in a certain subshells. For instances, the electron configuration of neon can be expanded as 1s2, 2s2, 2p2, 2p2, 2p2. For sulfur, it is 1s2, 2s2, 2p6, 3s2, 3p2, 3p1, 3p1. This expanded electrons configuration is best understood when you are already understanding Hund's rule, which will be discussed in another lesson. This number of elements are found to have electron configurations deviating from the expected. For instances, chromium has the electron configuration Ar 4s1 435 instead of the expected Ar 4s2 3d4. This phenomenon is attributed to the stability of half-filled 3d subshell. Migration of 4s electron is possible as this orbital somewhat close to the close of the 3d orbital. Same reason explained from the observed electron configuration of molybdenum, whose position in the periodic table is under chromium. This observed electron configuration of molybdenum is given by Kr 5s1 4d5. In the case of copper, the electron configuration Ar 4s1 3d10 is observed instead of Ar 4s2 3d9. Stability is attained when the 3d subshells is completely filled up, migration of a 4s electron to the 3d subshell. Silver and gold elements under the copper in the periodic table has the similar electron configuration. Aside from the elements mentioned, a number of transition and inner transition elements are found to have the anomalous electron configuration, and the reason from deviation from the expected is beyond the scope of this lesson. Valence electrons are the outermost electrons. They are found in orbital with highest energy level N. These are the electrons involved in the formation of chemical bonds. For element under group 1 has one valence electron, while group 2 elements have two valence electrons. For example, sodium, a group 1 element, noble gas, core abbreviated electron configuration Ne3s1, so it has only one valence electron. Calcium, a group 2 element, has a noble gas core abbreviated electron configuration Ar4s2, and 2 is the number of the valence electron. On the other hand, valence electron of a p block element under the period n are those in the ns and np orbitals. Given their noble gas core abbreviated electron configurations, neon has the 8th valence electron while sulfur has the 6th valence electron. As for the p block element under the period n, valence electrons occupy the ns and the n1d subshells. From the given noble gas core abbreviated electron configurations, chromium has the 6 valence electrons while rhenium has the 7 valence electrons. Valence electron of f block elements under the period n are given in the ns, n1d, and the n2f subshells. For example, cerium has a noble gas core abbreviated electron configuration on the right. Given this, the element has 4 valence electrons. Conclusion or the summary. Electron configuration is a notation used to show how electrons are distributed in different subshells. Ground state electron configuration consider that electrons are in their lowest state energy. Writing on the electron configuration will hold true of some elements. Bibliography or the references. Thank you.